Good afternoon. My name is Miras. I'm going to be talking about fixing bugs in binaries. And let's get started. So this is the basic agenda. I'm going to talk a little bit about the background about fixing bugs in binaries. Some of the examples that come up recently. Everyone's familiar with the WMF fix that xvid did. I think Alex is probably here in the audience, and he works at Determina. He did the Determina fix. There's an EI one. And I'm going to go over some strategy on how to go about doing this, and then I'm going to do a live example. If everything works out here, I'm going to be debugging live on the cell phone right here, fixing a bug in the camera software. So let's go. So how many times have you been using some third-party software that's only in binary, and you just find another bug and another bug and another bug? And it's like super frustrating. Sometimes there's no source available, or you have to compile a plethora of libraries and dependencies, and you need like an old libc, and then you need some other, I don't know, GTK library and all these other things to work all together magically. So you don't really have to do any of this depending on the type of bug. You don't have to depend on the vendor for their schedules to get around to fix something. You can just do it by yourself. And a lot of the skills that people have as reversers, they already have all these abilities, and it's just applying to a different type of problem. So the first thing you have to consider is bang for buck. How much work is this going to be, and what are you going to get back? And some bugs are really easy to fix, and it's very adaptable to binary fixes. Like some security bugs are especially pretty easy. Something that is not checking for bounds of a copy, or an off by one. Things that get a little bit more complicated are if you need to add, let's say, members to a class, you need to create new classes, stuff like that gets very complicated, and it might not be worth it. But another thing to consider too is if you have source, then perhaps you might want to do it the source route. But if it's a huge O-Day problem, and that's the only way you're going to protect yourself, then it is worth it to put in the extra effort and try to fix these problems. So some of the history of the third-party patches. The most common that everyone here is familiar with is cracks. Cracks have been around forever, and what do? They patch what some people consider software bugs. So a lot of the techniques that people use for writing cracks, the loaders, stuff like that, are directly applicable to this topic. So as I mentioned before, some other examples are the WMF patch, Alex's patch, the EI patch, and both these different security ones are for vulnerabilities that there were no patches available. So you have to go out and just make your own patch because you want to be protected. So this is the mantra I use. The least amount of change that gets the job done. This can mean that it doesn't necessarily mean the least amount of code change. There could be a couple functions that have, let's say, checks in them, and you could change those functions, and let's say that's X amount of bytes. But if you can change a central function that you haven't maybe noticed code path, and you change that, and that could be more bytes, but then you have a better fix. There's a lot of testing involved to make sure this all works, because not all code paths are known statically, and even dynamically. We can't test every single case. So a lot of times, least amount of change is the least amount of change impact into the program, not necessarily amount of code written. So this is the basic strategy that I use. First, you have to find the root cause of the problem. That means not looking at just one vector that has been reported, or let's say there's one exploit or one case that you know that this bug comes out in. A lot of the times, bugs only show up in, or only are tested or reported in one fashion, but really there's a root cause that it can show up in lots of different ways. The next step is you have to find this root cause in the actual disassembly before you can decide to make a fix. Then you're going to probably do some kind of proof of concept fix, make sure everything's working right, and you're going to test and test and test. After that, you know that this type of fix is going to work, then you're going to probably redesign and come up with a better solution. And once again, test, test, test. Lots of times, my experience has been that I write a fix and everything looks like it's working cool and I didn't test enough, and there's other cases I didn't think of, and I cause more problems to happen. I bring in more bugs myself. So that's one thing that you want to be aware of. So I'm not going to talk about like the different methods of applying fixes because they're pretty much well known. You can patch the actual file on the disk or flash if it's a phone or whatever type of writable media. You can also do runtime patching. You can inject code, have DLLs load up, use hooks, whatever. A lot of software comes packed now, so you have to use a hybrid approach, which is using a loader. So the loader will hook in after the binary has been unpacked in memory, and then it'll do changes at runtime, but it's also part of the actual file. So I'm going to attempt to do this live. I have slides in case anything goes wrong, but I'd really like to show it and show how easy it is really to do this live. This is my phone right here. And it's hooked up through ActiveSync. The USB cable is hooked up. I'm going to be using IDA for static disassembly, and I'm going to be using Visual Studio 2005 to do the debugging. Data Rescue does put out an ARM debugger. I did purchase it, but I'm going to use Visual Studio because most people don't have the ARM debugger, and it's probably the most used if you're going to do any type of debugging on a Windows CE on an ARM platform. So this is what this phone has. This has over a 400 megahertz ARM processor. And that's pretty crazy. I mean, I remember my computer was at 400 megahertz a few years ago, and this thing is running that fast. The camera is 1.3 megapixel. The reason I mentioned the camera is that's where the bug that I'm going to be fixing is, and we can move on. So. The Windows CE family is, they have pretty confusing terms. All these different 4 OSs are part of Windows CE. They all have very similar names, and a lot of times it's confusing, especially when I try to download software. Is it Windows Mobile 2005 Pocket PC or is it smartphone? All of them come from the same SDK though. So to do the debugging, all you need is Visual Studio 2005 Professional or higher, and the SDK is free from Microsoft. ARM does big endian and little endian. For Windows 2005, it uses strictly little endian. It also does not use the thumb instructions. A lot of the techniques that are applicable to regular Windows cracking are applicable to this because it still uses portable executables. The hooking is the same, and some of the same debuggers apply. So the bug on this phone is, it was reported in a lot of forums that if you took pictures with a phone and you try to mail them through using Gmail's POP3 service, that Gmail would not allow the attachments to go through. So people figured out that Google is actually doing some kind of file validation on all attachments that are mailed across, probably to prevent like WMF type attacks coming through Gmail and limit worms or whatnot. So there's some type of corruption in the JPEG header, and that's what we're going to take a look at. So now I'm gonna break away and actually take pictures with this, and we'll look at the image file and we'll figure out where the bug is, what type of bug it is, and go about fixing it. My phone has one problem right now that when you debug the camera, if you leave it running too long, sometimes it'll start messing up, and it requires a hard reset to get it back going. But since I'm outside my normal carrier zone, if I do a hard reset, I'm not going to get my Verizon content back, and my phone is going to be disabled for the rest of the weekend. So we're just going to have to pretend that the pictures are working. All the pictures you're going to see, they're going to come out all white or all black, but the bug is still going to be present, and we'll still be able to fix it, and we'll see it in the hex editor. this is active sync. It's hooked up to the phone right now, and we're going to start exploring the file system. All the pictures are going to come out in this folder. Alright, so this is the image opened up in the hex editor. There's some software that runs on the Pocket PC, which is imaging software, and it actually shows us an error message. So that's kind of the starting point that we're going to use to try to locate the bug. I have an emulator running here so we can actually see the screen. Oops. And I have a shared directory between the emulator and the main system, so we can run certain tasks on here. So we also copy the file over to the emulator. Let me just change the size on this so we can see it better. Okay, that's just, I guess, the small squares. I can't scroll down at the bottom, so I'm going to show you on the slide what it looks like when you open it up. So that's the error we get. It's corrupt JPEG data, and it says 17 bytes before some type of marker. And the next slide. So if I open this up on the phone, I open it in that software, and then I save it, it passes the Gmail test. I'm able to send it out. And doing analysis of the before and after, the only changes are in the exif header. The exif is kind of like an information header that's at the beginning of the JPEG. It'll tell you what type of camera was used to take the phone, what the date was. This extra information if you're, take a lot of pictures and you can organize and sort things. So the bug's somewhere in there. This is what the header looks like. The SOI marker, that means start of image, that's the beginning of the JPEG. The FFE1, that tells you that that's the start of an exif header. The SSSS is not for extra security screening, it's for the size of the data in the header. And that includes the 2 bytes for the size field. And after that, it's going to be ASCII for EXIF. So if we look at the file, we can actually see that in the header. Right here is the EXIF. There's the start of image, and here is the start of the EXIF data. So Hex Workshop has a feature that allows you to write structures. So let's say you have a file format, you write your own structures, and then you can analyze it, and it'll break it down for you. So let me load up a structure for EXIF. And then you just apply it here. So this is all the EXIF data. This first part, this is the SSSS, this is the size, and then it says it ends here. So if we look back at the slides, I have actual areas circled out so you can tell what areas actually are the different parts of the header. That right there is the size field. Here we see that the size is actually going into the next section. FFEO, that's the next section. And if you look 17 bytes ahead of that point, you see another FFEO. So that's the marker, that's the error that we're getting. So what do we have right here? This type of bug, we have an off by 1. So standard type bug that we see in a lot of security, we see in a lot of programs, whatever, this is what happened here. This is what's going on. So if we manually change it with a hex header and try to mail it across, boom, it works. So now we found the root cause of the problem. All it is off by 1 in the size of the header. So I'm going to go over a tiny bit of ARM assembly, just as an introduction, and what types of stuff you can get caught up on if you've only done Intel. And a lot of the stuff's pretty similar. This Earl at the bottom has a good short paper on an introduction to ARM assembly by someone at Microsoft, so it's specific to Windows CE, so if you're doing this type of work, all the stuff in there is very specific to it. This just talks about the register, stack pointer, whatever. And here's something that trips up a lot of people. Most of the time, assembly is like Intel, that it reads from right to left. But there's one exception. So first, it looks like regular Intel mostly. It's like move register to register from right to left, move an immediate 0 into a register. LGR is load, because it's a load store architecture, so that takes something from an address and puts it in a register. The instruction you have to look out for is the store. The store goes from left to right, so it goes from a register to an address. And that can be a little confusing when you first start looking at ARM disassembly. So what I'm going to do is I'm going to copy the camera executable from the phone onto the main PC, and then we're going to, I already have an IDB ready, so we don't have to wait for it. So the first thing I'm going to do is I'm going to try to look for the string EXIF to see if there's any reference to it, because we're trying to figure out how the header is created to figure out where the actual size is written into the buffer. So it's not here. There's no string like that. So there has to be another way that the data gets written out. And most likely when you're looking at writing binary data, you're most likely not going to use strings, because if you have to do string copy, you have to worry about terminating null, and if you copy with the null, without the null. So a lot of times for short strings like this, it's actually written out byte per byte. So in IDA, we're going to look for a copy, an immediate that represents the ASCII value for E, which is 0x45 into register, and then that's going to get stored in the buffer. So we do a search for immediate values, and then we're going to narrow it down to try to figure out where the copy actually occurs. So looking at this, really there's only two candidates available. There's this one here that moves it into R1, and here's another one that moves into R0. And what do we see? We see a 45 here, and then we see a 78, which is a code for the X. I, and F. So we figured out where it's actually being written out. So this is actually going to give us a lot of different types of information. When we load it up in the debugger, we know that it's reading it into R1, and then we look for a store byte, which is the next instruction, and now we know the address of the buffer. So now that we know the address of the buffer, we can look at the header and figure out where the actual write instruction is. And it's probably going to be pretty close to this. It's either going to be maybe in this function or called from a higher function, and it calls this and it does the other parts of the header because this function is too small to do the whole thing, and it'll be pretty easy to find. So that's the function we found. This is the sniffed out assembly code. Here's the header. Now, here's a cool paper. This paper shows how to, if you don't have source for something like this, and we don't have the source, you use Visual Studio and you set it up a certain way, and you can debug binary only. Usually the Visual Studio debugger is not configured to do this, but what you do is you copy the it's all in the paper. Basically, you build like a dummy application, copy the application you actually want to debug over on top of the one you just built, and then deploy it somewhere else. You won't have symbols, but at least you can debug, and you can do lots of cool stuff with it because you can. A lot of the DLLs in here are stored in the ROM, and you don't really have access to them. They're hidden, but if you just write a small program that loads up the DLL, you can start dumping memory, and you can actually extract a lot of these DLLs that they don't want you to see. So this is all set up already, and all we have to do is deploy it. And while that's going, let me move on to the next slide, and we'll talk about what the next step is. All right, cool. So it's loaded up. Is the font big enough for everyone to see? Is that cool?
Yeah.
All right, so we're gonna start this, and then we're gonna set breakpoints on the function that we already figured out, and we're gonna set breakpoints on the cross-reference to the function, so the parent function to that. So now we let it load up. It's actually loading up on the phone right now. So a couple things don't work perfectly right when you're using this debugger. You can't use this address screen to change addresses. It thinks that it's not available, so I just set breakpoint on anything and just change the location. And then let's see where so this is. All right, so the two breakpoints are set. Then all we do is take a picture. And then it hits our first breakpoint. That's the parent function. So we're right here right now. And so we see that this is where we just found out that it writes the excess portion. This probably writes out another part of the header. There's like string functions in here. And there's lots of string data in the header, so that's probably something. Here's time. There's time usually included in the exit header. And there's something else, but there's lots of stores. There's store bytes. And there's D-word stores. So it all looks like these are all different parts of the header. So after all these different parts of the header are created, we're also going to see a couple more stores down here that we should probably pay attention to. So let's continue on with the debugging. All right, so we're going to just go to the next breakpoint. I'm sorry, I guess one of the breakpoints didn't actually hit. Anyways, I'll show you the rest on the slides and see what we see. Okay, so this is what we just did. We set breakpoints on the actual function and then on the cross-reference, which is the parent. Now we're going to watch for the size being written. And once we identify where the size is being written, it's going to have 0, 0 at first because there's no size known. We keep on looking at the address location, and then we notice that these two instructions are going to write the size. The top one is going to be the most significant byte. The lower one is going to be the least significant byte. So that's here. After we've executed all these different header parts, these are the two things that we just saw on the slides. So now we know where the actual size gets written, and all we have to do is write a size that is 1 byte smaller. And that's what's going to be fixed. So the next part is deciding how to implement it. So all we have to do is put a branch in, and but first we're going to have to find some type of space within the binary to put this new code. So there's space between functions because a lot of times there's different types of alignment. So there could be sometimes 12 bytes, 16 bytes, depending on how big our patch is. We could use those areas. Another thing we could do is extend sections. PE headers for different types of sections, they have two different sizes. They have the virtual size, which is how big it gets loaded up into memory, and then they have the raw size, which is how big the size is on disk. So if the size on disk is bigger, then we can extend the virtual size to match that, and then we just have extra space left over, and we don't have to mess with any of the section or make a new section or anything like that. So in this tool, it's showing us that we have a difference of about, I think, 4 C bytes. So that's plenty of space to write a patch. So all you have to do is set the virtual size to be equal to the raw size, and you just have free extra space. And we do that, and then we create a patch. All the patch does is here, it jumps. They're essentially no-ops. They're not going to do anything. I just put these in here and copied part of the function down. And then I just put no-ops in case of any pipelining and things. I didn't want something to get partially executed. So all this does is it takes the data in RO, which is the lower significant byte, which is the size, and then it subtracts 1 from it, puts it in R1, and then R1 gets written out. Here's one problem that we encounter. When we load this up, it tells us that it's not, it's either signed with an untrusted certificate or something's wrong. This is because most of these binaries are signed code. And now that we've modified the binary, the signature isn't valid, so it's going to fail. And So all we have to do is, if the phone or the appliance or whatever it is allows for unsigned code, then we can just clear out the security section within the PE header, and then that's if it wasn't signed, or you can install your own certificate if you want, and then re-sign it. So here it shows the security directory. There's the RVA, which points into the executable, and the size. So we just set both of those to null, and it'll run. Here's the new image. So the new image that the camera produces now doesn't overflow the area by 1. It terminates before the FFEO, and when we test it, it'll mail through Gmail, and the bug's been fixed. But that was a quick fix. After more testing, we noticed that there's a problem with this fix. If the size happens to end in 00, when we subtract 1 from the lower byte, we'll end up with FF. So something like 00100 is going to become 01FF, and we just introduced another bug. So these are the type of things that you have to watch out for. Sometimes you'll do it and it works on your images, it works on your files or whatever, but you have to make sure that it works for all different types of test cases. So we can make a better fix without extending a section and only changing 2 bytes. And all that does is change these 2 values here from FV to FD. That's going to create a difference of 1 byte, and it'll work for all different image sizes. And there's no changing of section sizes, and you still have to change the certificate part because it won't match because you changed some of the data. So, and that's it. Just set those offsets, use the hex editor, and change those bytes. So I decided that I wanted to do a bonus patch. If you look at this data here, let's see, you'll notice right here that has my name in it. I don't want to post pictures with my name in it, you know. And it takes the name from a registry key that puts the owner information on here. So if I want to give someone my contact info, I want to have my real name on here, so if I beam it over to their phone or whatever, they can call me or whatever. But I don't want to have that stored in every picture I take that I post online or something. So we need to get rid of the artist name. So the artist name comes from a reg key on the phone. And this is the actual reg key, control panel, owner. So we go into IDA, we look in the strings, we find that, look for the cross-reference, and then we come across this code. So it's basically passing the key, then it calls some kind of wrapper that I've defined as get reg key to, and then it's going to check the return value, and then see if it's done or not. So all we do is change that, comparing it to 0, to change it to compare it against itself, so it's always equal. So essentially, it always thinks that there is that the reg key is blank. So your name will never be put in there. So that's just a 1 byte patch. So if you look on here, my name is no longer in the file. So that's it. We changed 3 bytes. We fixed 1 bug and improved the software. So what's the future of third-party patches? I think they're going to keep on coming out. Definitely companies are doing them a lot. I think advisories might come out now with binary fixes instead of having to first it. There's going to be different patches. And another thing I think might happen is there's this whole market for O-Day and for vulnerability stuff. So I think what's going to happen is people are going to sell the poison and they're going to sell the antidote together. That way you can protect yourself and your weapon can apply to other people and they don't have the antidote. So that's it. Is there any questions?
So you said you could change the certificate with the digitally summit?
What you're doing is removing a certificate. When you set it to null, you're saying that there is no certificate. So you either have to clear it out or you have to re-sign it with your own certificate.
Is there a way to sign those?
Yeah, the SDK comes with different tools to sign. You can create your own certificate, you can load it onto the phone, and then sign it yourself. There's tools included to do that. And you actually have to do that for different things like drivers. They don't let unsigned drivers be loaded in Windows Mobile. So if you write, go ahead.
I thought you had to send drivers to Microsoft.
That's for Vista.
Oh, okay.
For Windows Mobile, you can have your own certificates. And a lot of times, it depends on your carrier, because different carriers have different restrictions. I think one of the UK carriers, Orange, doesn't let you run unsigned code at all. Verizon lets you run whatever you want. Any other questions? All right, so my last slide is a little bit of shameless self-promotion. You can see me in Vegas, 2 shows. First one is at Black Hat. I'll be doing a training with my friend Matt Hargett on automating exploit detection, and I will also be performing at the Riviera at DEF CON 14, bridging the gap between static and dynamic reversing. I'm going to be releasing 2 plugins at...
Is it free? Is it training?
What?
Is it training free?
No.
This one.
Yeah, I'll trade trainings with people. At DEF CON, I'm going to be releasing 2 plugins for IDA. The first one is called PDB Gen. I reverse engineered the PDB file format, and you can take your IDA database and create PDBs. So if you want, you can load them up in, let's say, like WinDebug, if you're debugging drivers or whatever, and all your symbolic names will apply. I also created something called a redress, which does the same thing for ELF. I call it redress because Michael Zaleski released Dress with FemRest, and that was really cool, but it only did like library functions, and this does whatever you want. So that's it. I hope you enjoyed the talk. Thanks.